Good afternoon. My name is Mihaela Iordachescu. I'm from Material Science Department from Civil Engineering School of Polytechnic University of Madrid. And today I'm going to speak about fatigue and fracture behavior of high-strength Lath Martensitic steel that are conforming bars for press-stressing concrete structures. So my presentation is organized as follows. I will start with a brief introduction, then I will speak about materials and testing, then I will pass to the experimental results related to fracture toughness, fatigue resistance, and damage tolerance, and of course, I'll end with conclusions. Now, related to the introduction, today in civil engineering, we are using hot rolled steel bars for pre-stress construction. These are having high strength steel, higher than 1000 megapascals. These bars are obtained by quenching and tempering, and the microstructure is martensitic or perlitic. These are just two examples of the use of these bars. In this case, it was used in conforming this big San Francisco Bay Bridge. And then the other example is practically repairing a dam in Spain was repaired by using this type of bars. Since then, a new type of this high-strength bar occurred, and their suitability to be used in this type of high strength and this type of construction is investigated. So the objective today is just to determine the fatigue and fracture behavior of high strength Lath Martensitic steel. Now, related to the material, it is clearly that it belongs to hot rolled bars, 23 millimeter diameter, with a chemical composition which shows us that we are dealing with a medium carbon steel, but with a lot of microalloying elements like copper, nickel, chromium, and molybdenum. And with mechanical properties, tensile strength higher than 1,100 megapascals and elastic limit around 1,000 megapascals. Related to the steel microstructure, it is Lath Martensitic, and we found that it is quite fully isotropic. Now, passing to the testing, for fracture toughness, we used short bar specimen as per ACTM 1304, but we modified something to be sure that the crack extension is in the small scale yielding regime. Practically, we used pre-cracking from this chevron notch. For fracture and fatigue testing, we used the surface notch cylindrical specimens as presented here. These were subjected to distinct cyclic tensile loading steps at 8 Celsius, and then the crack size was monitored by stiffness measurements and, of course, optical measurements at the end of each loading step for fatigue characterization and also for determining the critical stress intensity factor Kc at specimen fracture. Now, related to fracture toughness, according to the standard, we used these equations. According to the data that it is plotted here, the load during testing and also load versus crack mouth opening displacement. Here we are having also the images of the broken specimen. The maximum load in this case was used in the equation, and from these 3 tests, an average of 75 megapascal square root of meter was obtained as fracture toughness. Now, related to critical stress intensity factor Kc, which was obtained after fatigue pre-cracking, practically by fracturing the cylindrical specimens, as it can be seen in this graph, the plots are given in load versus crack opening displacement. We used this other equation, and practically from these 5 tests, the average of the critical stress intensity factor is 82 megapascal square root of meter. Now, what you have to understand that here we are seeing large plastic deformation experienced by the specimens, and clearly this is incompatible with small-scale yielding. But the stress intensity factor computed with this equation is only 9% higher than the fracture toughness that we obtained with, let's say, standard specimens. Going further, to the fatigue resistance, here you have some images that are presenting the fracture surfaces of the tested specimen with the marked fatigue loading steps by heat tinting, because the tests were interrupted after some loading cycles, and the specimens were subjected to heat tinting. And at the end, we get the minor and the major semi-axis of the elliptical crack front. Thus, we plot the cracking front evolution with the fatigue cycles applied, and also the crack growth rate versus delta K. And thus we obtained that the tested steel fits a Parrish law with the same exponent free as most structural steels that we are currently using in construction. Now, the last part is dedicated to damage tolerance, to a failure assessment diagram, which it is plotted in terms of failure load versus cracked area. Here we are having with red dots our experimental results from the fracture test, and then we are having some theoretical lines that are indicating the first tensile bending plasticity controlled collapse. The second line is poor tensile collapse, and the third, which is in pink, is toughness controlled collapse for 80 megapascal square root of meter, and crack front ranging from circular to straight. So what we can say is that the steel ductility and the crack compliance of the tested specimens are enough to avoid their tensile bending collapse, but not the toughness controlled collapse. So now the conclusions. The experimental results shows that these practically Martensitic steel bars are endowed with a moderately high toughness of approximately 80 megapascals, obey to a Parrish law with the same exponent as most structural steels, and combines toughness and ductility in the due proportion high enough to prevent a brittle fracture in presence of severe stress concentrators. Thank you very much.